All right. So I want to start. I live my life dangerously, so I want to start the talk with something that's very, very scary to me. Because this is not my computer. All right. So this here is a web page containing, well, underneath JavaScript code implementing this prototype analysis that came out of this work. So on the left here, you'll have a program, and I better select the one that I prepared to start with. So here's one program in Google's Go programming language. It consists of, well, it declares two channels, A and B, and then consists of essentially two processes. For marketing reasons, these Go people call them Go routines. So this is the first process, and down here below you have the second process. And the first process, or the Go routine, will try to read from channel A and then subsequently write to channel B. And conversely, down here at the bottom, well, the second one will try to read from B before writing to A. Good luck with that, right? So what happened underneath the hood was actually that these warnings were generated. And there we have, you can tell it's, I'm on a foreign computer. Well, at least on my machine it says, read will not succeed. Damn it. And the subsequent ones says unreachable program point. So yeah, this is going as I planned. All right. Another example. This one again declaring two channels and now three processes. This first one writes a 1 to channel 1, a 2 to channel 2, and then what? Well, this one in the middle reads from channel 1 and then increments that value, writing it to channel 2. So when we get to the last process that tries to read from channel 2, well, we'll either get this 2 or the 2 arising from this computation, right? So it's supposed to illustrate this mixture of data occurring inside these processes and data being passed along these channels. So this will not give rise to any warnings which are displayed wrongly, sadly. If I press Analyze and scroll down on this machine that I don't know, you are welcome to study the ASCII dump, and you can confirm for yourselves that it actually discovers that Y is constant there. The last one is an example we took from a paper by Stadtmüller, Martin Sulzmann, and Peter Thiemann. That one has two channels and 5 of these Go routines. The first one just sends a number, 42, on the first channel, and the two next processes will do the same. We'll try to do the same, read a value from the channel, and then we'll write to the second channel whatever it received. And well, this one is competing to do that. Here's a fourth one, well, doing an infinite loop just to simulate some kind of work, I suppose. And then finally, the main process or Go routine here at the end will try to do 2 reads. And again, underneath the hood, our analysis discovered here, missing message, but this read here cannot succeed. All right. So with all of that, I hope to give you some idea of what we're doing. There's a what and a how to this work. The what is clearly some kind of static analysis of a subset of the Go programming language, in this case considering synchronous message passing. And the message is very much in the how here, because we're not doing a sort of classical whole program approach. Rather, we'll go for what we term a process local analysis against an environment description or approximate environment description. So thinking classically, an procedural analysis, or in this case, intra-process analysis, you would expect to receive as input the source code of the process that in question, some approximate description of the environment, and then, well, at least in abstract interpretation, we compute some approximate environments from which we can learn information about the variables at the different program points. So in this work, well, you can see that as extending that very classical setup, because we're also feeding it this approximate network environment description and subsequently computing or reading off, extracting some kind of network behavior as a result. Yeah, so in Go, I should say, they also, if you do full Go, they also have global variables, but, well, for the subset we consider, it's just only communication by message passing, which means that, the process code is not really going to change as we analyze, neither is the initial environment, so we can see that it really as this black box thing that for each process takes an approximate network environment description and computes a behavior for this particular process that we're analyzing. All right. So we can do that. Here's a setup with 3 processes. And so the way we then do inter-process analysis is then to say, well, yeah, we could potentially use the output here. But what we'll actually do is to take this computed network behavior of the first process and the third process and compose them, symbolically compose them. And well, we can do a meet with the previous input to ensure a decreasing chain of inputs, and then we can reanalyze. That's it. So if we start from some sound over approximation of the network, well, that could give us potentially a better approximation. So yeah, and well, similarly for the first process, we combine the second process and the third process's result, do the meet, reanalyze, and so on and so forth. Right, so that's one round more, and you can go on like that. So at any point we can stop. Well, as long as we started from something sound, well, if, as you saw the tool, if it discovers something that should give rise to a warning, well, we can stop. We don't need to refine anymore. All right, so that's the setup. To pull something this crazy off, what do we need? Well, we need some kind of abstract domain for expressing the network environment and behaviors. We need some kind of operator, a symbolic shuffle operator, it turns out, to combine the analysis results. We need, well, to come up with a way how to extract the network behavior from one single process we're analyzing, and, well, furthermore, well, if you're one process in the middle, there can be a couple of other processes where one is reading and another is writing, and those will synchronize underneath your feet. So you have to take account for that as well. All right. So, scary word, lattice-valued regular expression. Well, perhaps not scary, but at least long. So let's just start with the regular expressions. Here's a regular expression as I think most of you who have operated a Unix command line would recognize, some string of digits ending in a 0, right? So if you agree with me there, I claim, then you also understand lattice-valued regular expressions, because this can be seen as a lattice-valued regular expression over the domain of intervals. And intervals is something we all had for breakfast, right? So interval 0 to 9, clean star, and this 0 here we can represent just as singleton interval 0 to 0. Well, intuitively with the meaning that you would expect. So that's the domain we'll use to capture these behaviors. Formally, we had a SAS paper 2 years ago describing how, well, if you fill in a Galois insertion, lattice-valued regular expressions is, well, like ordinary regular expressions, but where these characters, the L's here, are taken from the abstract domain with some additional requirements, I should say. So the meaning of a lattice-valued regular expression is then, well, a structural definition over this thing, of course. And when we hit one of these elements from A, well, we need to fall back on the gamma, the concretization there. All right, so that's the domain. So that particular domain, well, there's not, well, there are multiple elements that have the same denotation but are syntactically different. Here's one such. So we have to do the standard quotienting up to denotation to regain a lattice structure. Yeah, in parentheses, it's not a complete lattice though. All right, so as a domain operation over this thing, we consider the derivatives, Brzozowski derivatives. I'm sure I'm pronouncing that wrong. So intuitively, if you, by analogy to finite automata, where you move from one state to another, recognizing some character, this is really the regular expression equivalent. You move from one expression denoting a language to another, recognizing some character. And the question is then, well, what are the characters? And that's in the lattice valued setup. Well, it turns out a nice answer to that is atoms. So here's an example for you. So atoms are these smallest inseparable, so smallest elements inseparable from bottom. So here, classical parity lattice. We can do a derivative. Yeah, so in that setup, the atoms are odd and even. We can do a derivative with respect to the odd atom here of, say, that regular expression, and you get something which I hope you will agree with me should denote something that arises from this one once we have read, or I recognize one odd character. Yeah, and that whole thing, of course, generalizes to sequences like the original Brzozowski derivatives. All right, so Brzozowski back in '64 proved there are only finitely many derivatives up to associativity, commutativity, and idempotency of the plus operation. That also holds for the generalized version. In practice, however, we throw in a few more simplifications. So say simplifying empty plus anything to the anything, and you saw, well, how that could come in handy to simplify something like that. All right. Turns out, well, a lot of these derivatives really yield the same. So here's one example over the intervals now. So if we derive with respect to the atom 0, 0 of this regular expression, well, we get this one, but so do we for 1, 1, and 2, 2, and 3, 3, and so on. So all of these are the same. So that suggests, perhaps we should group them somehow. And well, how about forming a partition of equivalence classes? And that's really the job of a range operator that says, okay, give me one lattice-valued regular expression, and I'll return to you some partition so that I'll only put 2 atoms in the same equivalence class if the derivative with respect to both yields the same. Okay, so now we also have the equivalence classes or the partitions, so we need more operations to operate over those. One is just getting a representative atom out of one of these equivalence classes. Another one is overlaying two partitions over each other. There's a lattice ordering there, and depending on which way you order the lattice, you can see that as a join or a meet. All right, enough lattice-valued regular expressions generally, but for our purposes, if we want to do the network analysis, well, we can then use them as follows. So suppose we number the channels there. So I'll just use an interval there to describe what channel we are writing to, and then the analysis as formulated is parametric in the abstract value domain. So here we have val hat. Similarly for the read domain, we do the same thing. And then what? Well, then we do a Cartesian product of these two, and that will really be the channel domain, which we throw in as the parameter domain to the lattice-valued regular expressions. And then you can express something as ugly as this element. So 1 says, okay, this is the first component, so that's part of the right. So to the channel numbered 1, I'm writing, or the environment, say, is writing something odd repeatedly. Whereas the left side here denoting reads, that's bottoms. So yeah, intuitively that's the kind of thing you can express. So all right, 1 down, 3 to go. Shuffling, the operation. Well, syntactically, we'll extend the grammar of regular expressions with a symbolic shuffle. Well, what's the denotation of that? Well, it turns out this shuffle operation has a well-defined meaning. We did not come up with that. We just reused existing work, say by Salzman and Thiemann. So the denotation of one of these symbolic shuffles is really this shuffle of their denotations. The derivative over a shuffle like that distributes nicely onto the two, and you can prove that this is correct. The finitely many derivatives also still holds with this extension, and well, we'll throw in a few more shuffle-like simplifications. So if you shuffle with something empty, that's empty. If you shuffle with the epsilon, you get whatever you had initially, and the rest of the operations are adjusted accordingly. All right.
Is your domain closed under the shuffle operator? I mean, you again get an LVRE when you shuffle two expressions.
Yes. Well. Well, syntactically, yes, right? I just write it. I glue two things together. Yes. Yeah. Of course, in the limit, because of. I'll leave that for later. All right. Extracting network behavior. So the analysis is phrased as in this constraint formulation that Hannon Fleming and Chris Hankin advocate in their book as a cache. So traditional formulation that associates to each label not only an approximate environment or store, but also one of these lattice-valued regular expressions. Of course, we in this room understand something like that as a postfix point. The first of the two, the curly E, you can view as, well, E for entry. What have we discovered upon entry to analyzing this statement? Curly X for exit. Well, what have we discovered holds prior to analyzing the thing? So that setup nicely lets us again partition caches into per process pairs, say curly EI, or 1 and x1 for the first process, and so on. And now I'll go through every single character on this slide. No, so I just want to point out here, as part of this, I would argue it's a relatively standard formulation, but you see there's curly D's here, derivatives occurring, and well, it does what you would expect, I argue. The read case, it's a structural definition. The read case will perform a suitable derivative with respect to the right component of that character domain, and vice versa for the right. So how do you then read off something like that? Another simple structural definition. I'm not just going to go through it. It returns a pair. Well, for this setup, I just need to glue the two LVREs together with a plus in order to get the complete behavior. All right, 3 down, 1 to go. Sorry? I'll get back to that. Because otherwise I will definitely not have time. That's a pretty short talk. I count 21 minutes here. All right, so the closure constraints, again, express this concern that we had, that if we have one process and 2 other processes communicate underneath our feet, one write matching up with a corresponding read, well, that shows up as these reads and writes with respect, so in a derivative formulation. So closure under read followed by matching write and vice versa. All right, so those are the pieces. Soundness, well, I only get, 23 minutes? So one of the biggest challenges of this work was, well, coming up with a name, right? So the Go subset, we are not the first to carve out a subset, and some of the others that came first, they had a bigger subset, so we had to come up with an even smaller name, right? So that's the Nano Go name. We phrase structural operational semantics using this traditional idea of annotating arrows to describe network actions. So this is at the process level, and then at the system level, we can say things like, okay, process I is performing a tau step, or process I and J are communicating the value V over channel CH. And then we use this operational semantics to prove soundness. That's complex, but there's a trace here with a number of network actions. So if you take anything away, well, suppose I'm process I, then the rest of the world, well, if I suitably project out away my own actions, if to see, okay, what is the rest of the world? If that's solidly accounted for in the right cache entry, then what? Well, afterwards, if I satisfy the analysis constraints, if I do a suitable derivative with respect to this sequence of actions, is included at the right entry in the cache. So of course we'll satisfy something like this by just including top clean star in the first entry. So the soundness of the iteration comes from this part that then again says, well, for a trace, and if I already have something solidly accounted for, then that same thing I can actually express as one of these symbolic shuffles that involve that extracted history thing. So if it's there, we won't lose it by doing this composition. That concrete behavior will still capture it. All right, so prototype, I did not write this in JavaScript, trust me. Instead, I used a compiler to compile OCaml to JavaScript. The code is there. Currently, it's a bit more than 4,000 lines of code. I should say this is, I consider this a proof of concept. So for one thing, it's really walking the abstract syntax tree. Of course, it would be more efficient to extract equations and solve them to eliminate this interpretive overhead. These closure constraints I mentioned, we do by a local fixed point computation. And well, starting from, well, worst case, well, we improve at most of 100 times. Here's a few benchmarks just to break it up. I showed you some of these examples. 2 to 5 processes, 1 to 3 channels. Stabilizes after, well, for these examples, at most 4 inter-process iterations in under a second, which I don't think is too bad for this proof of concept. Of course, this whole setup is not geared towards analyzing for deadlocks. So because, say, the dining philosophers example could potentially also succeed, right? We don't catch that because of the over-approximation. Yeah, so this thing is a composition of a number of things. There's a symbolic operator. You can also see it as a principle or an algorithm, if you will. There's a soundness proof of the approach. And then we have this proof of concept prototype for this process local analysis applicable to this subset of Go. I admit completely this is proof of concept, but I still consider it promising. So thank you for your attention.
We can start. Andreas was first, and then.
Yeah, so I would like to come back to my question about the LVREs.
Yes.
So they are, I mean, when you compose 2 of these LVREs, you get again an LVRE.
Yeah.
And you talked about this fixed point iteration, so you have a fixed point test. So you have an ordering that you can check.
Yeah.
So I assume this ordering amounts to subset inclusion for the denotation.
Mm-hmm.
And so I'm wondering how you implement this check, because obviously the subset inclusion is undecidable. So I'm wondering what do you
Subset inclusion is undecidable.
between the LVREs, yes.
So for regular expressions, the ordering is P space complete.
Yes, but then when you add the shuttle, the shuffle operator.
Uh-huh.
I mean, where is Zach? Is Zach here? No. Huh? Shuffle is all right? Yeah? Okay. And what's the complexity with shuffle? Okay.
You had me nervous there.
Next question. Next question here.
Okay. So to answer the question of, so I said widening, but you have a descending sequence with narrowing.
Yes.
And so you don't need to check exactly for inclusion. So you can have something which says it's either included or I don't know.
Yeah.
So that answers the question of, because you will stop at 100 iteration, which is a stupid narrowing.
Can you repeat the last part again?
Yes, your narrowing is you stop after 100 iterations.
Well, of course, I stop early, right?
Except if you could check before that you had inclusion, and if you are not exact on the inclusion, you will stop anyway at 100, so it works.
But we agreed that with this shuffle, it was not undecidable. It was still decidable, right?
This you don't care, because
right, Zach?
It will work anyway. So you should refuse to answer this question.
No, but I just think that, well, the
okay.
condition for the question was, this is undecidable. Zach tells us it is decidable, right? Okay, it may have a horrible worst case time complexity.
And so the real question is why?
Let's get
why
to the real
do you
question.
go top down, which is because you will be blocked by any fixed point, and what you need is the least fixed point. If you go from bottom and over approximate, you might arrive at a better approximations.
Yeah, but as it's set up, because a read does a derivative with respect to a write and vice versa, it's sort of a chicken and egg problem. If you start from the bottom,
Yeah, you will have longer and longer stuff. Maybe you have the right, it matches nothing, the other will go on, you will match, you simplify, you go on.
no, but that's really the synchronization as it is expressed in this setup. It could probably be done differently, but if I'm analyzing a read as part of trying to go up, I try to do a derivative of bottom, and I get.
No, you will have some initial state with maybe an initial regular expression that will be longer and longer. And when you have match, you will do the match. So
Yeah, maybe
you have no
continue
answer,
offline.
but I think it should work.
Are there any other questions to Jan? So I was just wondering, sort of typical Go programs, how many processes will they involve?
Yeah, that's also that's a good question. Of course, the whole thing as currently set up is one file. Typically, these span multiple. I don't know. It would, of course, we should investigate and see. I was talking to Sok Young Ryu, who also have investigated some of these regular expression-like domains, and she was considering subsets. I think that could also inspire, say, a whitening for this domain or something like that, in order to let it scale to, a lot of processes.
Okay, if there are no other questions, then let's thank Jan again.